Might be useful to hear again. If you recall, we looked at these three pictures yesterday, and I think the day before yesterday, modulo this class, I think that was a Friday. We won't be looking at this picture tomorrow because tomorrow is a flex day, but on Thursday, we'll definitely be looking at this picture again, and I will be accompanying it with the following words. Integration is multiplication, but one of the factors is continuously variable. So here we have kind of three stages of what's going on. In the first picture, the length is constant over the entire width, so we get to use multiplication. Here we have constant length, we get to use multiplication. So that constant length means we just get to use multiplication for the whole area. Area is equal to length times width. In the second picture, our length is variable. We have variable length, but it's constant in short bursts. So here we have variable length. But constant in short bursts. So in this case, we get to use multiplication in short bursts, then we have to add. We use multiplication in short bursts, then use addition. So no problem. Multiplication is just fast addition. It's repeated addition when everything's the same. We get to use multiplication. If things aren't the same, then we just use addition. Notice that I could break the previous case up, the constant length. I could have 1 times 3 plus 1 times 3 plus another 1 times 3. So we don't need to do all that, or sorry, 1 times 5 plus another 1 times 5 plus another 1 times 5. So since we're adding 1 times 5 the whole time, we could take 5 times the 1 plus 1 plus 1. We factor out the 5. We get to multiply. So we're really doing the same thing in both of these. So thinking of this one in the constant length in terms of the variable length, this is like 1 times 5 plus another 1 times 5 plus another 1 times 5. We can factor a 5 out because algebra. And that's the 3 times 5. So we're really just doing the same thing. We're just doing the fast version of things. That's what multiplication is. It's just addition when everything's the same. Multiplication is just addition when everything is the same. In that third case, the length is variable and continuously variable. So in this third case, we have continuously variable length. It's always changing. So this is a problem because we don't have anywhere to put the plus signs. I can't say add up all the values of the function because there's nowhere to put the plus signs. That's the problem with continuously. There's no next real number. So that's the problem with continuously. So that's the problem that arises when we have continuously variable length. There's nowhere to put the plus sign. So we do the same thing that we always do, not just in calculus, but in math classes everywhere. Go back to the previous problem and adapt that for the new problem. That's all we're ever doing. Just take what we've done before, adapt it to fit the new thing, and then see what happens. It's like experimenting. Mad science. So what we're going to do is we're going to use the previous case. And here's how it's going to work. We're going to assume that the function, that the length is constant in short bursts. We're going to go back to the previous case. That's our strategy. So strategy. Go back to the previous case. What that means is that we're going to assume that the function is constant in short bursts so that we could use multiplication in short bursts, then use addition. Then make the short bursts infinitely short. So in the previous problem, or sorry, in the previous case, the short bursts, the length was constant for a short burst of 1. We're going to call the width of that short burst delta x for some change in x. So we're going to assume f of x is constant in short bursts, say delta x, where our f of x is going to be the length and the delta x is going to be the width. Once f of x is constant in short bursts, delta x, we get to use multiplication on those short bursts. Just like we did in the previous case, because that's all we ever do. Go back to the previous case and adapt it for the new case. So then we're going to use multiplication in short bursts. Our length is going to be f evaluated at some x. Note that I'm writing x with a subscript of I. I'm going to use a bunch of short bursts. So there's going to be an x1, an x2, an x3. These are the places we're evaluating the function. That's where we're going to make them flat on top. And then we'll multiply by our delta x, which is going to be the width that we get from the previous case. That's what we did in the previous case. Since the length was constant in short bursts, we got to use multiplication in short bursts. Next, we just add up all the areas. Next, use addition. So what we're going to have There's going to be an f at x1 times the delta x, then an f at x2 times the delta x, and so on until we get to however many rectangles we're making. Let's say n. When we don't know how many, we just say n rectangles. So the way we note that is we're going to say plus dot 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 plus f at xn times delta x. There are the areas of n rectangles, n short bursts where we just use area is equal to length times width. And once we multiply and find these areas of all these n rectangles, we just add them up. So f at x1, x2, these are just x values that we pick from each of the short bursts, and we evaluate the function somewhere. Yesterday, we used the left endpoint for the underestimate and the right endpoint. So yesterday we had x1 was 0, x2 was 0.5, x3 was 1, x4 was 1.5, and that was our underestimate. When we did the right estimate, x1 was 0.5, then x2 was 1, and so on. Those are our 4 x's that we picked. Evaluate the function. That's what f at x1, f at x2, f at x3, and so on means. And that's what we're using for the height. That flattens out the height. And we use that height for some short burst, delta x, that we use for the width that I wrote in blue, which should have been in green, because I'll switch to green. Really missed the boat because I could have used the blue and then the red. Then when I put them together to make an area, it would have been purple. Missed opportunities. What does blue and green make? Blue, green? Green? Blue. That's not how colors work. You don't just match up the two English words. People that speak German are like, oh, why not? I love German compound words because you just like, they just mash all the words together. Great. You know exactly what they're talking about. So here's what we're going to do. We want, just look at how much space that takes up. We have fancy notation for saying adding up a bunch of things with an index. So the I is an index. So here's where I is equal to 1. Here's I equals 2. And we do this 3, 4, 5, all the way up to I equals n. So we have an index. That's just labeling things. 1, 2, 3, 4, 5, and so on. So we can summarize this with summation notation. We use a capital sigma for sum. There's an index. And then we just write the form where we plug in the index. So we write f at x sub I times delta x. So the sum as I goes from 1 to n of f at xi delta x would be the way to write a summation for this expression up here. We could read this sigma. So we use a capital sigma for a sum. And so we say the sum as I goes from 1 to n. That's how we would read that notation. The sum as I goes from 1 to n of f at xi times delta x. Should include the of part. That's how we read that notation. The sum as I goes from 1 to n of f at xi times delta x. It's important that we see that f at xi is the length, delta x is a width. So that expression, f at xi delta x, is an area. And we're just adding up all the areas. Any questions? Lot going on because it's new notation. Now this is going to be an approximation of the area with the continuous length. We know that we improve the approximation by using more rectangles. Because instead of that, it's just taking a higher resolution of our continuous curve. We're starting off with, we get this high, this is high resolution. Right now we're at like a Game Boy Advance level. Worse than that, this is like a TI-84 level of resolution. You can see the individual pixels. As our processors get more powerful, we can throw more pixels up on the screen and use a higher resolution. And what all that happens is the little boxes get smaller. And we just make sure that the little boxes get so small that we can't tell the difference. This looks continuous to us. We look at a circle on our computer screen and say, that is a circle. And meanwhile, the computer's like, all idiots think this is a circle. It's just a bunch of boxes. But the resolution is high enough that we don't know. So we know that we improve the approximation by using more short bursts. So improve the approximation . We can improve the approximation by using more rectangles. So calculus just says use infinitely many rectangles. And there's our revenge on the computers. Where's your high resolution now, computer? We can imagine a continuum. Can you do that? I thought not. Hey, computer, think of a random number. No, don't just pick one from a list. Come up with one on your own. Yeah, can't do it. We shouldn't be so antagonistic with the computer. They do things that we can't do. We do things that they can't do. We should get along and make each other stronger. I don't know why there has to be some kind of robot apocalypse. I think it's because humans are kind of dicks towards everything. So it's not surprising that we're going to be mean to our computer. I apologize, computer. You're an extraordinarily useful tool, and I could not do my work without you. I don't think that's enough when the robot apocalypse comes for the computers to be like, well, no, he's one of the good ones. I think they're like, well, he was better, but all humans must die. I mean, it's a robot apocalypse. So what we're going to do is take our approximation and give it the exact value by making a Riemann sum. Now it looks the same, but we just add the calculus part to it. And the calculus part just says, use an infinite number of rectangles. N is the number of rectangles. So let's just take the limit as n goes to infinity. We would plug in infinity, but we're not allowed to just plug in infinity because infinity is not a number. So we take the limit as n goes to infinity. At which point people are like, oh, isn't that just how you plug in infinity? And I go, quiet, you. But yes, that's how you plug in infinity. Also note that I'm already using my lazy sigma. Each Calc 1 class gets exactly one properly written sigma with a little serif on it, with a little whoop, whoop. After that, they're all just backwards threes. At this point, you're like, oh, don't you write lowercase epsilon the same way? And I'm like, oh, quiet, you. But yes. So up here, n is the number of rectangles. Yesterday, n was 4 rectangles. Or in the first example, n was 2 rectangles, then we went to 4 rectangles. And now we're at infinitely many rectangles. Any questions? This whole page of notes is just us thinking about how this works. And the notation that we use to express the thinking that goes behind this integration process. Now, at this point, if I asked you to calculate the area under a curve and above an interval, even if I told you what that curve was, we would be ill-equipped to deal with that, especially if I said, find the exact value, or find the value to 12 decimal places if you can't find the exact one. Then you'd be like, oh, but my calculator only goes to 10 decimal places. And I'd be like, oh, well, that's unfortunate. Actually, what I would do is I'd give you false hope. I would say, find it accurate to 10 decimal places. You'd be like, oh, all right, my calculator has 10 decimal places. Not if the first part is, the first 3 digits are taken up with like something over 100. And you go, oh man, I only have 7 left. Well, I guess you're going to have to do some other work. Right now, you wouldn't be able to do that. We're ill-equipped to find exact values of these areas. We need to be equipped to find these exact values. But before we can do that, we have to understand the thinking behind this integration process. We got to think of we're trying to find the area under a curve, but and we're just going to use length times width, but our length is being continuously variable. So we're going to drop back and assume that the length is constant in short bursts. Then we'll get to use multiplication in short bursts. So we get f of xi times delta x. And then we just add all those up. Sum as I goes from 1 to n of f of xi times delta x. Then we pull out the calculus and just use an infinite number of rectangles. The limit as n goes to infinity of the sum of as I goes from 1 to n of f of xi times delta x. F of xi times delta x is just length times width for area. That's how we get the area under a curve where the length is continuously variable. Now we just need to replace area is equal to length times width with whatever we have. Distance is equal to rate times time, but our rate is continuously variable. Same argument. Replace length with rate and width with time. Work is equal to force times distance, but our force is continuously variable. Replace work with area with work, length with force, width with distance. It's all the same. Applications of integration are just applications of multiplication. Integration is multiplication, but one of the factors is continuously variable. This is how we think our way out of the problem. It is not how we mechanics our way out of the problem. We don't have the mechanics yet. Any questions? Comment? Yeah, it is still foggy outside. That's why I saw someone, I think, pulled the shades down so they're not reminded of it being foggy outside. It might just be that they don't want to have to watch people do archery because that looks fun. I don't know, because from this side of the building, you can see the archery class. I don't know if you know that, but there's an archery class here at Skyline. And they practice out there. That's what that big thing is with the hay bales. So students be like coming onto campus, it's like, oh man, I've got to go to physics. Where are you going? Fucking archery practice. I'm gonna shoot a bow and arrow at stuff. And you're like, oh, people? No, just hay bales for now. For now. One year I went to Cub Scout camp. This is back when I was in Cub Scouts. And one of the classes in Cub Scouts, I don't know if they do this anymore. They're like Super American. Now, I don't know if you know this when you're a Cub Scout, you're like what? 10? You're like 10. One of the classes that they were offering to 10-year-old boys was shooting. No, not bow and arrow, like with a rifle. So like you go to Cub Scout camps, like, oh, what classes would you like to take? There's whittling. Well, okay, there are like a lot of classes. These are the ones that our little 10-year-old boy minds focused on. One of them was whittling. It's like, oh, that's cool because it involves a knife. So they're going to be handing me a knife. That's dope. I like that. All right. One of them was archery. It's like, oh, that's even better. I get a bow and arrow and I'm going to learn how to shoot a bow and arrow. Heck yes, I want to do that. Robin Hood, here I come. Let's fold up some paper hats. Folding up paper hats was one of the classes, but we're like, oh, we only want this one to make paper hats to go shoot a bow and arrow like Robin Hood. But then we saw the one that everybody wanted, the one that filled up fastest, and that was shooting. And they're like, oh, this shooting thing, is that like with cameras? And they're like, oh, no, that's with guns. And so like everybody signed up for that. I'm like, oh, that's awesome. We have to sign up for that. When is that one? 8 o'clock in the morning. I'm like, oh, we see you. I see your game, you rogues. That's how you're going to get us up in the morning, isn't it? Yeah, it worked like gangbusters. Everybody was up so they could go to shoot guns at 8 o'clock in the morning at 10 years old. No, we didn't, surprisingly. Not when I was there. They're actually very serious. Like most of the classes, it was just like teenagers were running the class. Just like, you know, like camp counselors. If there was going to be a horror movie that started, it's just a bunch of teenagers that were going to get murdered. But at the shooting, they actually had like adults. That was like where they had adults, and they took this shit seriously because they were handing 10-year-olds guns. And I can't imagine. I can only imagine that the first reaction was like, "Oh, wait a second, you're going to hand 10-year-olds guns?" Like, is my insurance paid up? Well, all right then. So they were very serious about things. But yeah, and they were single shot bolt action 22 long rifle. And we learned, that's when I found out how bad my eyesight was. And they're like, "Oh, just line up this little thing with the little thing on the front with the thing that you're shooting at." What am I shooting at? That little circle out there. What little circle out there? On the paper? The paper? Like, "Oh, you have glasses?" I'm like, "Oh yeah, they don't work very well." So anyway. So I was like looking down range. I'm like, "All right, aim at the circle." I'm like, "Oh, which one?" "The one in the center." "No, which one in the center? I see two of them." You're like, "Oh, aim for the middle." Anyway, what are we talking about? Oh yeah. They put shooting at 8 o'clock in the morning to make sure we would all wake up. And it worked. It was so sneaky. Any questions on the thinking behind this? We need to understand the thinking behind the integration. Integration is multiplication, but one of the factors is continuously variable. The way we deal with it is to take continuously variable and make it constant in short bursts so that we can use multiplication. And then we just add up. The weird thing is that we're adding up over a continuum. There's nowhere to put the plus signs because there's no next thing. So we model our continuum with an indexed set. This is a discrete set. We model it with an indexed set where we can put the plus signs and think, what happens if we just have an infinite number of terms? How's everybody okay? What this becomes is what we call a definite integral. We go from writing a capital sigma to this integral symbol. Like a smooth S looking thing. If you've seen the cover of a calculus book, there's usually a violin on the front. So this is shaped like that, like an F hole on a hollow instrument or a semi-hollow instrument. And what we're doing is we're doing the integral of f of x. Notice that this f of x is the continuous f of x, no longer indexed. And our delta x, our width, since we have an infinite number of rectangles, our delta x is infinitely thin. So we stop using this delta x because that's too big. And we say it's dx, just like we did. With our derivatives. Slope is delta y over delta x. When delta y and delta x become infinitely small, we write dy over dx. That's the same thing that's happening here. Delta x is too big. When it gets infinitely small, we write dx. When our function goes from being indexed to continuous, our delta x goes to dx. Now over here in the integral part, since there's no index, that's not what this is going to represent. So here we're going to write the integral from a to b. And these are values of x. Those are the endpoints of the interval on the x-axis. So notice those are x values. These are the values of x that we're imagining plugging into the expression f of x dx. We're evaluating f of x dx at all these values from a to b, and then adding up the results. Even though it's weird to say it that way, because where are we going to put the plus sign? Remember, the idea is we want to find the area under a curve and above an interval on the x-axis. So we would say that this is the integral, the definite integral from a to b of f of x dx. That's how we would read this symbol. This is the result of this Riemann sum. The definite integral of f of x dx from a to b. Specifically, x equals a to x equals b. You want to think of the integral symbol saying all the things what you're going to plug into the f of x dx. It's important that you think of it this way, because next semester in Calc 2, at the beginning of the semester, when we're talking about definite integrals, I'm going to do the same thing. And I'm going to have the same three pictures at the top. It's still going to be 5 times 3 or 3 times 5. And it's still going to be a 3, 4, 5 over a 1, 2, 3. And the shape of the function is still going to be this shape because it's the only shape function that I can draw generically, I guess. And I'm going to say this integral from a to b, the definite integral part, that's just a list of all the x values that you're going to plug into the expression f of x dx. And I'm going to remind you that it's weird to think of it this way, because if that's a continuum, where do we put the pluses? And we're like, oh, it's calculus. Forget it, Jake. It's calculus. Question? It's going to be super important that we understand it that way, because when I start changing what this expression is, instead of f of x dx, when it becomes something like f of x and y dx dy, then our integral needs to tell us a bunch of x's and y's to plug into the expression. So the integral is telling you what you're going to be plugging into the expression, and then applications of integrations like, oh, well, what are you going to do with that expression? Area is equal to length times width. Now you've covered everything. Everything where there's multiplication. Just length times width. Distance is equal to rate times time. Work is equal to force times distance. Gross pay is hourly wage times hour. Now keep in mind, you still don't have the mechanics, because I haven't told you how to find these definite integrals. But if you need an approximation, your calculator can. I just did. For the most part, when your calculator can do something, I just say, your calculator can do the thing. And you're like, oh, really? And then the next day, people just know how to do the thing. Dr. Google will help you. All right. There's no class tomorrow, so that's it for today. I will see y'all on Thursday. Everybody have a good couple of days. And thanks for playing.
Bye. Nice. Day.
Yes.